All right, so here we go, starting chapter 2. But before we give it even to algebra, so remember I said chapter 1 was really a review of pre-algebra? Chapter 2.1 is still a review of pre-algebra with like a lot more variables into it. And so what we really want to see here is this whole concept of similar or like terms. And before we get to equations, we're still going to simplify each side of the equation with like terms. So we don't want to confuse those two. That's probably one of the more confusing things in chapter 2 here. So let's go for it with the time left. So can we simplify or combine these like terms? And so what does it mean to have a like term? First of all, it has to have the same exact variable and has to have the same exact exponent on that variable. So in this case, 5x plus 4x, those are like terms, right? So in this case, how about a 9x? Notice the exponent does not change on your variable, right? It's x to the 1 power here. X to the 1 power still stays x to the 1 power. The only time a variable changes is when you're multiplying. We'll get to that a lot later. All right. 8a subtract 12a. Anybody?
Negative.
Perfect. Negative 4a. All right. How about 3 in a row here? How about 12y subtract 7y plus 5y? I go with that here. 12y subtract 7y will give you 5y. So you still add another 5y to get 10y. Okay, good there. Too easy. Okay, now let's mix it up just a little bit here. So now you got to look for the like terms. And again, hopefully you guys have already done the pages prior to lecture, right? So let's go for it here. 2x and a 4x make 6x. And sometimes what we do to represent like terms, we do these little bar lines here. So the one with the single bar, those are like terms. Double bars, those are other like terms. In this case, how about 6x plus 1? We good? Cool. Going on to the next one here. Again, single bars, 8a subtract 2a. And then sometimes we add squigglies just to make it a little different as well too. But anyways, it's all the same. How about 6a plus 10? We good? All right. And then if you get so sophisticated, you don't even start putting the bar lines down. You're like, Mr. H, I know it's the 9x minus 2x, 7x, 4 minus 1, 3, done. Almost expert over here. Okay. All right, let's throw in some distributive property and then also some simplifying here. So don't forget that 6 has to multiply the 2x, has to multiply the minus 7, but don't multiply it to the negative 4 because that's part of the little parenthesis. So here it is, multiplying through. I get myself an 18x minus 42. That's just for distributing the 6. Still have to mess with that minus 4 at the end. So let's see, what is negative or a minus 42? Subtract 4 more going to give you? Negative 46. I go with that. All right, so notice you can't add these together anymore, right? Because the 18 has the x and the 46 doesn't. All right, that 46, we actually call it something called a constant term, or a constant number here. Okay, number 4, the one that messes up a few students here. What should we do first, anybody?
Distribute.
Distribute. You have to distribute before you can subtract the 5 and the 2. In this case, distributing the negative 2 there. 5 is all in front, still stays there in front, but negative 2 times 3y, negative 6y. And then negative 2 times 1 is a minus 2. Okay, once you get rid of all parentheses or all distributions or all multiplication, now you can add or subtract, but 5 minus 2 is a 3, so...
4. Is it okay if I put 3 minus?
Perfect. Was waiting for that question to happen here. Question is, Mr. H, can I put the 3 in front? Absolutely. So you can write it like that, or you can write it as 3 minus 6y. Those two are perfect. Or it's kind of funny. Just write it like that. Oh, good. I did. All right, get a little more sophisticated. How about 2 distributed properties here at the same time? I know. Not tough for you guys, I totally understand. All right, so distributing the 4, everybody need to here, so 4 times x, 4x. Distributing it to the -3 or -3 makes a -12. And again, this little weird thing here, if you just see a minus sign, technically it's almost like a -1 being distributed. So how about a -5x? And for the last one, how about just a -6? All right, like terms to put together. I think the 4x and the -5x makes a -x. And then
About the x being negative, I don't know what I learned is wrong, but well, I was once told that it's a negative x, you should put 1 in front of it.
Cool.
But,
The question is whether you should put a little negative or whether you put a little 1 here in front of x. Not really.
you don't have to, doesn't matter. Okay, I think
Negative.
it's just my teacher's preference. I think maybe she liked it.
Yeah, negative x is just perfect to put down. All right, how do we get a negative x? Is because we had a positive 4, then we had a -5, right? So $4 in the checking account, and then the $5 fee comes in, and then you're in trouble. Then you got yourself a -1 in the account. Okay, so that was all about simplifying. We do that a lot in mathematics. We do that, as I said, on one side of the equal sign. So kind of careful. Notice there's no equal signs here anywhere, right? We're just simplifying, simplifying, simplifying. Once you start moving things across the equal sign, that's when things kind of get a little different, okay? But if you're just simplifying on one side, then do what we do over here. Okay, the other part that we do in algebra is the whole concept of plugging in variables. I think we did a little bit of this in chapter 1 here. So find the value of the following expressions by replacing the variable with the given number. So other math textbooks will just say evaluate the variable, or evaluate the expression. Just means you plug it in. All right, so this little 5x minus 2, we want to evaluate this by knowing what x equals. If x is equal to 3, what is this all going to give us? And so what we do is we plug in that 3. All right, what I usually do is whenever I plug in a number for my variable, I always put parentheses around it, because then I know exactly what I plugged in. I know exactly what stayed the same. So 5 times x, notice I didn't need parentheses here, but right here I do need parentheses because I want to signify that they're multiplying each other. All right, so in this case here, 5 times 3 is 15. I got rid of my multiplication rule, and then I simplified down to 13, 15 minus 2. Okay, should be pretty easy here. B is all yours if you haven't done so already. All right, and this is probably another common mistake I see Math 61 students make here. Let me show it to you here so you always know not to do it. And again, this is the whole concept of why we put parentheses here. If you were to plug in this -2 into here and not put parentheses, look what happens here. It looks something like this. See that? Notice, like, oh, it's 8 minus 2. It's not. It's supposed to be a multiplication. So that's why you do need this extra parentheses all the time. You need it's 8 times -2 plus 4.
But if we can keep it straight in our head, that's okay, right?
That's cool, yeah.
Yeah, because what I did at first, I put just 5 times 3 minus 2 with what you thought for 5 times 3, and then the second one I put parentheses because I know.
Perfect, yeah. If you keep it straight in your head. And some students, what they do is they'll multiply already in their heads. 8 times -2 is -16. They'll do that already, and then they just add the 4.
So you don't have to write it all out? Or would you prefer?
I think it would be preferable, so then you know exactly what you're plugging in. And then you can always look back at your work here. But everybody okay with a -12 at the end of it all? Cool. Okay. All right. Sometimes what we do is we plug in the x in more than one spot. All right, that's what C and D are all about. So instead of collecting the like terms first, many times we'll say, okay, you know what? I need to plug in a -1 for x. I'm just going to plug in both spots at this point. And so when we do that here, careful with the negatives here. So notice the x's now become all -1 in parentheses here. Now let's multiply. Let's see. Looks like it's going to be 3 times -1, -3. This guy's going to stay the same. And then this one's going to be 5 times a -1. Now in this case, 5 times a -1, I think about it as going to be a subtraction. Or you could think of it as adding a negative. Either or. If you wrote it like this, that's fine. Or if you wrote it like this, that's fine too. Remember how we always want to change things back to addition. It's just a lot easier for us to sort of think about what's going to happen. Hey, then I also notice here that all this stuff is all negatives, right? It's a -3 and then plus a -2 plus a -5, all that's being added together. So in this case, this part here, -3 plus -2 is a -5. -5 plus -5, how about a -10? All right, you guys get D. If you haven't done it already, go for it. Give you extra little time. Finish off yourself real quick. All right, plugging in this 6 into this x here, as well as into this x over here. So how about 5 times 6 -7 minus 2 times 6? All the multiplication we need to do here between the 5 and the 6, also between the 2 and the 6 here. So about 30 minus 7 minus 12. Again, this point, this is where you sort of have to think about, do I need to change it to addition or just sort of just keep it a subtraction? Do I know what 30 minus 7 is going to give me?
Could we do like, or not like, but start with the negatives, like add -7 and -10?
Ah, good, good. So here it is. Please excuse, and then this is going to be repeated here. Notice multiplication and division we do at the same time, right? Just whichever one we see first.
Same with addition.
There's subtraction. So the first one that we see is right here, 30 minus 7. That's the first thing we see as we look from left to right. So that's going to be 23. Then 23 subtract 12.
But you get the same answer to this better. I got the same answer. But I started with, I did 30 minus 19.
Question came up is, Mr. H, I got the same answer when I did 7. You did, let's see, what you did here is you did
-9. -19.
Yeah, you did a whole bunch of stuff in your head. Hopefully you know what you did in your head, because you definitely did this here. You did that real quickly here.
Yeah.
And then you did that real quickly, and then you added these guys together. And then you did that. So yeah, the technically is correct. I'm just thinking if you keep on doing it, you might just start. Okay, a little bit more complicated here because we have exponents now. So let's plug in that 5 in for the y. Should look something like this. Notice the little 2 there. All right, with that said, no parentheses to simplify, but we do have exponents right here. So this means 5 times 5. This becomes a 25 over here. You know, I'm going to multiply as well because they're disconnected from each other. Right, the exponent was different from the multiplication, or away from it. So I can do those at the same time, as long as they're not connected. All right, then from here we go. It's going to be 25 subtract 20 from left to right. Gets us a 5, and 5 plus 4 gets us a 9. All right, and Mackenzie, this is where things can get haywire. If you did the 20 and the 4 first, then you're going to wind up with some wrong answers. Letter E.
Yeah, I did the same thing.
Okay.
But I didn't put the parentheses. I did this little dot.
No problem. All right, number 7. How about two different variables at the same time? Now I have an x and a y that I'm plugging in. So let's plug it in here. So the x becomes a -3, the y becomes a 4. So it should look like something like this initially when you plug it in. All right, in this case, multiplication, 3 and -3 make a -9. 5 and 4 make 20 with a minus sign in front. All right, if you're going to keep it like that, that's fine. Probably what I would do at this point, I'll probably just change this to a plus sign, right? Make that into a negative. So -9 and -20. -29. I got -29 and a +2. Anybody?
-27.
Perfect, yeah, go with it. -27. Oh boy, so let's go with multiple different variables, x and y, and also exponents at the same time.
On this one, I put the x and y side by side.
Mm-hmm.
And that's what.
All right, let's go for it here. So as you plug it in, notice inside the middle term there, it's 5. In parentheses, you got a 2, and in parentheses, you got a -3. All those, understand that's all going to be multiplication with us here. All right, is the multiplication connected to the exponents? Nuh-uh, right? Because here's the multiplication here, and there's a little minus sign just sort of sitting out in front of you. So we can do this all together here. So it's 2 squared is a 4. Put the minus sign down originally, but when we start multiplying out everything here, it's going to be 5 times 2 is 10. 10 times -3 is -30, so negative of a negative is a positive, so I'll have a +30. At the end, ooh, this is fun. -3 times -3, +9, cool. So at that point, just add them all up here. 4 times 30 is 34, and then 34 plus 9 more would make 43. 9 is a cool number to multiply with.
Because you can do the finger thing, and then if you add the two numbers you get for the answers, you always get 9.
Mm-hmm.
So I think that's the coolest thing. Even though it's very odd. And then it's also, you can square root it, which is even better.
Yep. Kind of fun. Some fun properties there.
Just like the other numbers, I think the whole
All right. Besides that, another thing we're going to do in algebra is this whole concept of sequences, especially when we start graphing. We're going to say, okay, if this is the first number corresponds to this. Second number corresponds to this. Third number corresponds to this. So this whole concept of sequences and plugging in stuff to see what the correspondence between two values here. So let's do like a quick. So let's do this here. Let's substitute 1, 2, and 3, and 4 for the end value. And what we want to do is we make a little, it's called a correspondence. But if n is 1, then this expression is this. If n is 2, an expression is this. That sort of gets us prepped for chapter 3 here. So let me do the first one here. If you say n is equal to 1, if n is equal to 1, I'm going to plug in that 1 into my expression here. So 2 times 1 plus 3. And 2 times 1 is 2. 2 plus 3 is 5. So in that case, I get my answer is 5. We good? So now n is equal to 1 corresponds to 5. Let me just keep on doing the rest of the way here. So if n is equal to 2, I'm going to plug in the 2 for the n value. 2 times 2 is 4. 4 plus 3 is 7. And then, yes, we should see a little pattern happening here. If you see a little pattern by the time you get to 3, then you're good. So the n's are really, a number starts with 1 going up by 1s. The expression is actually a number that starts in 5 goes up by 2s, right? All right, so n is equal to 3. Hopefully you guys got this one here. It's 2 times 3 is 6, plus 3 more is 9. There's our 9 again.
Doing this, you could probably make any kind of pattern.
Just depends on the expression that you use. You can make any kind of pattern here. Okay, n is equal to 4. Plug it in the 4 here. 2 times 4 is 8, plus 3 more make 11. So there it is. Correspondence is if n is equal to 1, that's 5. If it's 2, then it's 7. 3, 9, 4, 11. Okay, so let's take a look at one here where usually students get confused on here. So there's two different expressions. This whole concept of multiplying by 3 or cubing something. I think the example problem in the textbook is multiplying by 2 and squaring something. But for our practice problems, it's 3 here. Yes, Math 61 students sometimes get these mixed up here. So let's just kind of do the whole part here. So if n is equal to 1, what we're going to do is we're going to plug in that 1 in for our value here. And if that's the case, right, if you plug in 1 in here, 1 times 3, just the 3, right? So n is equal to 2. 2 times 3 is 6. N is equal to 3. 3 times 3 is 9. So notice it's just a multiplier by 3, right? Again, n is equal to 4. 4 times 3 is 12. So notice also they go up by 3 each time, huh? So 3 plus 3 is 6. 6 plus 3 is 9. 9 plus 3 is 12. All right, but how about this one? N to the third power. What does that mean? Yeah, times itself 3 times, right? So if it is n is equal to 1, that means we have ourselves as 1 times 1 times 1, which is 1. If n is equal to 2, which means 2 times 2 times 2. 8 is good, right? All right, this one, okay, here we go. 3 times 3 times 3.
27.
Sweet. And then the fun one here, 4 times 4 times 4.
64.
Cool. All right, if you got that, you're doing really good here. All right, for 2.2, we're going to learn one property. 2.3 is another property here. So now we finally got to algebra. All right, before we get there, we've got to do a few things here. First of all, what in the world does it mean to have a solution in algebra? For something to be a solution, which means it's that number plugged in that make the statement true. So in this case, since you have an equal sign, this equal sign says now that this side of the equation and this side of the equation better be exactly the same when I plug in this value. Good? If 7 is a solution, it makes these both sides the same. So let's try it here. Let's see, if I plug in a 7 for x, would it make all that to be true?
No.
No way. Plug in a 7 gets me 7 times 3 is 21. And 21 subtract 1 is going to be a 20, not a 19. So really, 7 is not a solution to this problem. What we tend to say is we just tend to say no.
So we don't have to write it out as a, like, because I don't know if that's considered a word problem.
Not a word problem, but we're just sort of considering what in the world is a solution. What do you mean by solution in algebra?
Okay, just making sure, 'cause I'm not-
Okay, for 2, is -4 a solution to that problem? go for it. Let's see. Plugging in -4 in for x. Should look like this, right? 8 minus 3, and in parentheses a -4 equal 20. We're just checking here for now. All right, what I tend to do is if I have a subtraction symbol out here, I tend to think of this as like a -3 times a -4. I just think of these as negatives because they sometimes are interchangeable here. So 8, how about plus 12? Ooh, is that right? 8 plus 12, 20? Yep. So there it is. Yes, 20 does equal 20. Therefore, -4 is a solution to this problem. Again, we're just sort of building this whole concept of vocabulary here. So what is a solution? Solution is a number that makes the statement true. In terms of equal signs, it has to make both sides the same to each other. That's what equal sign means. When we get to inequalities like less than or greater than, they don't have to be necessarily equal to each other anymore, but it still has to be a true statement. So one concept, what is a solution? All right, another concept here is something called equivalent equations. What does it mean to have an equivalent equation? It means that you have the same solution set. So that means the answer does not change in a sense. So we have a few things here, and I'm not particularly like the way the book sort of has put this. The question really here is for number 3 is this: is x plus 5 equal to 8? Is that an equivalent equation to x equals 3? Well, we already know what the answer is, right? For the second one, we're trying to determine if these guys are equivalent equations here. Does what works here, does it also work here? And let's go for it here. So if I say x equal to 3, obviously 3 works here, right? If I'm going to plug this 3 back into here, 3 plus 5 makes 8, and 8 is equal to 8. So yes. So the x equals 3 works for the second equation, x equals 3, or plugging in 3 works for the first equation. Are we good there? So notice 3 was the answer to both of those. Okay, how about B? So for the second equation, a is equal to 19. That's already solved for, right? That is actually saying that a does equal 19. Now the question is, does 19 work here as well? So as I take this 19, plug it into 19 minus 7 equals 12. And it does, huh? 19 minus 7 is 12, and 12 is equal to 12. Perfect. Okay, so yes, those are equivalent equations here. And that's what we want to do in algebra. In algebra, what we really do is we make equivalent equations as we go all the way down and to finally solve for what we want to solve. All right, last one of these here. C has 3 different equations. Y plus 4 equals 18, y minus 4 equals 10, and y is equal to 14. Are those all 3 equivalent equations? I have to go to this last one here that's already been solved, obviously. For this one, I don't know what the solution here is. I don't know what the solution here is, but this one's already been solved. So I'm going to say, okay, if y does equal 14, I wonder if 14 is also an answer for this guy, and I wonder if 14 is also an answer for this guy. And so as I plug in 14 over here, 14 plus 4, does that equal 18? Sure does. Cool, so okay, we got those. Now the question, that middle one over here. 14 minus 4, does that equal 10? It sure does. So because 14 works for all 3 equations, we consider those guys to all be equivalent equations. Okay, so here it is. Whole concept of solution, whole concept of equivalent equations. Now let's start with algebra officially. The first rule of algebra is this whole concept, well, even before that, the whole concept of algebra is that you have an equation. Notice you have an equal sign now. You have two things on the sides of the equal sign, right? You have an A on one side, A, and a B on the other. This is one property that works in algebra, works all the time. This whole concept of the addition property. That means I can add same number to the left-hand side as well as the right-hand side. I can still keep my equal sign over here. That's really the question. Can I keep my equal sign? So here's what we're going to do real quickly here. We're going to go back in our mind to pre-algebra. This is going to be problems from my head, okay? I'm going to see if it works in pre-algebra, it has to work in algebra. We good? If the numbers work out, therefore I can work it out with variables. So don't need to write this down, but you're going to think with me here, okay? Everybody okay with 5 is equal to 5? If I were to add any kind of number whatsoever to both sides, can I still keep my equal sign? Like this right here. If I had to add 4 to both sides. Yeah. Since they're equal to originally, and I'm adding the same exact thing to both sides, at the end, I'm still going to get the same exact thing on each side. We good there? Kind of feels weird at first, but we'll actually see some cases where actually it does not work. That's why. This one, of course, is the easy one. It's going to work. So how about this one? Let's take a look at let's take a look at subtracting something or adding a negative. Will still work if we add a negative here. So 7 is equal to 7. How about if we add -4 on that side, -4 on the other? Can I still keep my equal sign? That works by me. Still can keep my equal sign. Okay, how about if we start off with the negative already, and then we start adding something else? Let's see what happens here. Again, I can pick any number of the whole entire planet. I'm going to just pick 8. So my question is, can I still keep my equal sign? Yes. Absolutely. There it is. Okay, so this is called the addition property of equality. In English, it says adding the same quantity to both sides of an equation will not change the solution set. Or if you want to say another way here, adding a number to both sides makes equivalent equations. You still get the same answer. All right, so let's go for it here. So for number 4, what should we add to both sides to get x all by itself? Yeah, see how we have a -7 over here? I want to get rid of this -7. The only way I can get rid of this -7 is make it go to 0. So if I do this, if I add 7 over here, remember how we learned in chapter 1 a -7 and a +7? If you add its number and its opposite, those two will cancel out completely. So if that's the case, those are gone. Notice I'm using the addition property of equality. I'm adding the same number to both sides. I'm adding the opposite of this guy because it's going to cancel this guy off. So that's gone. X is now all by itself. 11 plus 7 makes 18. You have those equivalent equations? Yeah. By adding only the same number to both sides, at the same time, we have made equivalent equations. So therefore, x equals 18 is equivalent to this. Therefore, x equals 18 is a solution to this guy. Okay, see how that all fits together? Making equivalent equations, get x by itself. Whatever x is, because we made equivalent equations, 18 is the solution set. Okay, of course we got to throw in fractions into here. So a plus 1/2 is equal to -4 of 5/4. What should we do here to get a by itself? Perfect, I go with that here. Subtract 1/2. So it's going to be -5/4, subtract 1/2. Oof, I'll let you guys finish that one off, if you haven't done so already. All right, let's see. I need common denominator, which is 4. 4 is good. First of all, I probably want to just change it to addition, so then I have to change it later here. But yeah, common denominator of 4. That means I have to multiply this guy by 2, this guy by 2. And how about a -5/4? Add a -2/4 makes a -7/4. I made an equivalent equation. The answer is -7/4 for this guy. Therefore, negative 7/4 is a solution to that equation. Okay, are we good there? Does that all make sense there? I'm kind of throwing a little tough ones at you here.
That's the toughest one. That's like.
How about 6 and 7? Got some decimals now. So on let's see, on the left-hand side, I see 8.4 plus x. I see this side, I see a negative 1.8. So it looks like what I want to do is I want to get rid of this 8.4 over here. Because if I can cancel this off, I got x by itself. So subtract 8.4. Let's see, and then I notice that both of them are negative. I have a negative 1.5 and a negative 8.4. So let's see, both negative. I just add them up, put the common sign. Is that right? So there it is. 5 plus 4 is 9. 1 plus 8 is 9. They're both negative. Put a little negative sign. Because I'm technically doing addition property, right? I'm actually technically adding both sides by a negative 8.4. All right, for 7. Okay, here's one little thing we're going to do here for 7. Is notice on either side of the equal sign, not moving things across the equal sign, but just on this side here, can I combine anything together?
Negative 2x and 4x. You can subtract.
That would work. So negative 2x and 4x. Notice we're not moving anything across the equal sign, right? We're just simplifying this side of the equal sign. So negative 2 and a positive 4 makes positive 2, so 2x plus 3. And before we do that, let's look to the other side here. Can we combine the 7 and the 4 on this side? Mm-hmm. Yeah, so notice what you do is you just do what we did in the beginning of 2.1. You're just simplifying. In order of operations. Okay, now at this point, now when you start solving for x, so when you start moving things across the equal sign, that's when you need to put a little negative, or that's when you're trying to cancel stuff. So when you yourself are trying to move things across, that's when you want to cancel stuff out here. So 3 and negative 3 are gone. 11 minus 3 is an 8. All right, dividing through by 2. Oh, sorry. We haven't learned that yet, huh? That is going to be called the multiplication property. But real quick here before we even do that, we kind of ask ourselves this. What number times 2 would eventually give you 8? 4. That's an easy one to do by that right away, right? We will learn in the next section, instead of just thinking about it and guessing what that number should be, what we can do is we can just do the opposite. What is 2 doing to the x? Multiplying. What's opposite of multiply? Division. Let's just divide both sides by 2. Here's what happens. What's 2 divided by 2? 1. So our whole goal will be to get x by itself. In this case is to divide out whatever number is multiplying x, so it becomes just a 1. 8 divided by 2 is a 4. There it is. So that's called the multiplication property or division property. Technically it's multiplying by 1/2, but we do it quickly with just dividing. All right, I got some more for you guys to simplify before we start moving things across. So for number 8, we've got to simplify this whole entire side over here. So I'm looking at this here, forgetting the equal sign for now. I'm thinking to myself, okay, I got to multiply this 3 over here, the 3 over here first. So 12a minus 3 minus 10a over here. All that is good. On the other side, 3 minus 8. We'll get to that shortly. But anything to simplify on the left-hand side still? The a's, huh? 12a minus 10a, 2a. And so notice the minus 3 just sort of stands there. Doesn't have anything here. On this side, it's 3 minus 8. And if you can think about it here, again, $3 in the checking account, subtract $8, that means you have a minus $5 in the checking account. All right, if that doesn't make sense here, then we can always do it like this, make that into a plus, And then you're thinking, oh, that's right, they're different signs, I have to subtract. 8 minus 3 is 5. Take the sign of our bigger absolute value number, which is 8, which is a negative. Okay, now we're ready to move things across. So what should we do first? Plus 3 to both sides, perfect. Leaving us with 2a on that side. Negative 5 plus 3? Perfect. All right, what number times 2 gives you a negative 2? What number times 2 would give you a negative 2?
Negative 1.
Negative 1, that's perfect. Okay, if you did it that way, that's cool. If you divided by 2 on both sides, that's cool too, because negative 2 divided by 2 is a negative 1. Okay, on this one, let's see. Notice we have x's on both sides now, right? You got a 5x on one side, a 4x on the other. Here's what we've got to do. We have to use the addition property to cancel one side of those x's. Usually what I like to do, I like to cancel the right-hand side and move all the x's to the left. So there it is. So I subtract 4x because that guy's a 4x, and then I just cancel this one. Whatever I do to one side of the equation, I got to do the other. And so for 5x minus 4x, that's just going to be a 1. Don't need to write it down. The positive 7 comes down, the equal sign comes down, and then negative 7. All right, what should we do now to solve it?
Minus 7.
Perfect. Now we're trying to get rid of this 7 here because it's extra on the side with the x. So subtract 7 from both sides. Finally, this is going to cancel this out. And then what is negative 7 plus another negative 7? That works by me. X equals negative 14. All right, moving on to the multiplication property. So last time we learned the addition property. Now we will move on to the multiplication property. So I wonder if it's the same. If I were to let's see, last time I was supposed to add the same number to both sides. This time I want to multiply the same number to both sides. If I get the same thing, I'm doing good. Okay, we're gonna do what we did last time here. I'm gonna pick some numbers from my brain, okay? See if it works. And if it works for pre-algebra, it has to work for algebra. Cool. So you guys just have to agree or disagree here. 5 is equal to 5. Everybody agreed? If I were to multiply each side by the same exact number, can I still keep my equal sign?
Yes.
Absolutely. In this case, just for an example, I'm going to multiply both sides by 4. If I multiply both sides by 4, I get 20 on both sides. In this case, absolutely, I get to keep my equal sign. All right, let's see. Just to test it out some more here, let's see. How about we multiply through by a negative number, just to sort of see what happens here. So 5 is equal to 5. Let's multiply through by a negative 4. Does my equal sign still stay? Yeah, it's negative 15 on both sides, right? Okay, and here's a fun one here. I'm going to put 35 is equal to 35. True, what do you guys say? Okay, here's the little sneaky part here. I'm going to do a few things here. Technically, I should be multiplying both sides by a certain number. So technically, I want to multiply by 1/7. Notice this is technically multiplication, is that right? But really what I'm going to do between the 7 and 35, I'm going to divide them, right? I'm going to ask myself, you know what? How many times does 7 go into 35? 5. So really, that's what I'm going to do right there. But notice dividing by 7 is the same thing as multiplying by 1/7. That's how we sort of get away from it, or get away with it here. So both sides still equal. What do you guys say? Yeah, both sides could be 5 is equal to 5. Okay, so in English, here we go. So multiplying both sides of an equation by the same, ooh, there's one little thing here. It says non-zero. So the little number we can't use is 0. Can't multiply with 0. So multiplying both sides of an equation by the same non-zero number will not change the solution set. Okay, so now we know adding, and now we know multiplying. Let's try this. Okay, and the multiplying could be division, right? We could be dividing, thinking about it as multiplying a fraction. All right, let's go with it here. So I want a all by itself. What's the negative 8 doing to a? Multiplying, huh? So how do we get rid of a negative 8 that's multiplying a? Divide. Let's divide both sides by negative 8 over here. And then we're going to do negative 8 over here. All right, on the left-hand side, what happens? Hey, I think we learned this here. Negative divided by negative? Positive, is that right? And 8 divided by 8? Just a 1. So really what we have is we just have the 8's cancel, leaving us with just an a in front. 40 divided by negative 8 gives us a negative 5, and we're done. Okay, we're good there? That's the multiplication property. Okay, this one's a little more fun one. Let me rewrite this here because I don't like the way it's sitting there. I'm going to write it as negative t over 6 is equal to 2. Let's see, I don't like fractions here, so let's do this here. Let's multiply both sides by 6 over 1, or just 6. Bless you. All right, so let's do this here. Let's multiply, whoa, that's a lot of multiplication. Okay, let's do this here. Let's multiply this guy by 6, and let's multiply this guy by 6. And on this one, I'm going to actually just say it's going to be 6 over 1. Okay. So what's going to happen to 6's on the left-hand side? Canceled, canceled. Awesome. I get one step closer here. This guy's now going to be negative t. And 6 times 2 is 12. Okay, good here? All right, now there's kind of 3 different choices here, just depending what you want to do, depending how you've been taught here. So negative t is equal to 12. How should I get t all by itself? Anybody? We can divide. What number should we divide by? You don't want to divide by your variable. You want to divide only by the number that's multiplying the variable. What's the invisible number multiplying the variable, sort of, kind of? Kind of, sort of 1. I go with negative 1, is that right?
Oh, yeah.
So, real quickly, I can just do this. There it is. Because what's going to happen
It's
is...
not 1, I don't know what it is.
It's a negative 1, right? Because if you put a 1 in here, technically it's the multiplication is still by a negative 1, not a positive 1. So, the negatives cancel. Dunk, dunk. I'm left with t is equal to... Anybody got an answer? Negative 12. Now, I just want to show you something just real quickly here. You don't have to divide through by negative 1. This is one of those special times where you can do a few little things here. Because it's a negative 1 right here, you can actually just multiply both sides by... So instead of dividing, what we do is we multiply by negative 1 right here. Because what's negative 1 times negative 1? Still a positive, right? The whole point is just to get rid of the little negative there. 12 times negative 1 is negative 12. Cool? Or, as Mackenzie said, you know that this guy's negative, right? So what we can do is we can just sort of change the sign on one side and change the sign on the other.
The way I look at it is if the 2 is positive and both the numbers are on the top side and the bottom side of the t and the 6 are both negative in my head. I do that. I just turned it, I make t, like I put negative 12 on top of the 6 and negative 6 on the bottom, and then I just know.
Let's go for it. Let's go for it. The question is, because this little minus sign in front, this little minus sign has to go either to the top or to the bottom, but it is not going to go to both. So it's either like this. Just want to correct something here. Or it's like this, but it's not going to be a negative t over negative 6.
But you still get the same answer if you do it that way. Because technically if you divide a negative by a negative.
And I'm going to differ on you with that just real quickly here. And the reason for it, if you make both of them negative like this, and you multiply through by a negative 6 like this, notice what happens here. The negative 6's cancel. And so notice what you got. Is that the same thing that we got earlier? No, we got this extra negative in there, right? That should not be there. So whenever you see fractions with a little negative in front, like say 3/4, you all.
The equation wasn't that complicated. When it gets more complicated,
Yes, when it gets more complicated, then we got some trouble.
Yeah, but I changed my rules.
Okay.
I know. I just did.
Okay, got it. As long as you change your rules.
Yeah.
All right, number 3. So notice now we have a fraction in front of us. It's 3/4. Why? Just to show you here, there's kind of 2 different ways to do this. And we'll go from it here. So if you have a fraction that you're trying to get rid of, this would be the slow way, and then we'll do a quicker way here. So if some of you guys get the quicker way, that's cool here. So first of all, this is the slow way. Let me write this over again here. So 3/4 y equals 9. First things first, do you see a fraction anywhere here? Yes. The denominator is 4. Let's multiply by 4. That will just get rid of fractions. Hey, that's right. Can't we just multiply by any number we like as long as it's the same on both sides? So we're going to use 4 for the special reason, because this 4 is going to technically cancel off that 4 on the bottom. Ooh, I like this multiplication rule. So that means whenever I see fractions, I can technically just multiply through by denominator. 4's are gone. I'm left with 3y is equal to 9 times 4, which is 36. Right. At that point, then you can say, okay, what number times 3 gets you 36? Or you can just divide both sides by 3. Let's divide both sides by 3. So cancel, cancel. Y equals 12. Okay, anybody know the quick way of doing it? The one-step method? Multiply by? Let's see. Starts with the recé, ends with the precol. Yes, cool. How did you guys get that? That was cool. Okay, we look at our fraction, and all we're going to do is we're going to say, look, I'm going to multiply by the reciprocal. I'm going to multiply by 4 over 3. Because what's so special about that? The fact that both those numbers are just going to cancel. Just going to do the same thing on the other side here, but here we go. 4's are gone. Good. 3's are gone. Good. Well, the thing is, sometimes we do have to make a little fraction over here. Let's see. This is kind of fun too. Notice that if you do 9 times 4, you're going to wind up with 36 over 3. Right? Or what you can do is you can cancel off the 3 and the 9, or reduce down the 9 down to 3, and 3 times 4 is 12. So there it is. You get same thing both ways. Cool. Out of curiosity here, just a little vote here in the class here. How many say, Mr. H, I like the first way. I like it step by step. I like 4, get rid of fraction, divide. Cool. 1, 2, 3, 4. How about Mr. H, I like the second way. I like the one step. Boom, done, over with, see you later. Cool, okay. All right, and then I figure 2 people either sleeping or, let's see, Mr. H, I hate both ways. Or Mr. H, I love both ways. No, they're sleeping, okay. No vote, okay. Abstained. Number 4. Number 4, let's see. First things first, we're going to simplify as much as we can on each of the sides before we do anything else, before we start running across here. So 8 minus 12. minus 4. On the other side, whoa, on this side I just have x's here. So 5x plus 15x, 20x, and 20x subtract 4x. Perfect. Good there, 16x. Divide both sides. Ooh, okay, another weird thing is, hold on. My x is actually on the right-hand side. And I know Mr. H told us earlier that I'd like my x to be on the left-hand side. We'll see what that is. But if you have the x on the right-hand side, keep on working it so x is by itself. So if you see a 16 multiplying x, just then divide both sides by 16. Good there? Let's see, I think 4 goes into both those, right? So let's divide the top by 4. Let's divide the bottom by 4. And we got ourselves negative 1/4 x, negative 1/4 is equal to x. Okay, so how do we move it around? Easy. We just put the x on one side and then the negative 1/4 on the other, and we're good to go anyways.
You got off this say there.
So again,
it has to be negative 1/4.
It'll have to be a negative 1/4, yeah. Another way you can write it, so notice the negative is sort of up there with the 1. That's one way to write it. I guess another way you can write it is like this. And what you do is you put the little negative in front of the fraction. That's another way you can write it. So it's negative either on top with the numerator or negative in front. Fraction itself. All right, these next two problems here, all yours here. Just a quick practice problems here. Number 5, very easy. Move whatever you need to go to move across. You get x by itself. All right, here's what I'm going to do. I'm probably going to subtract 9 from both sides to get that 5x by itself, and negative 6, adding a negative 9, I think that would make negative 15. Both are negative, so just add them up, put the negative sign. All right, divide by 5 on both sides. How about x equals negative 3? And how about show of hands real quick here? How many got that one correct? Number 5 is A-OK. All right. Number 6, 7x is equal to 4x plus 18. Notice that 18 is all by itself, right? It's the constant term.
It's not by
18.
You mean
Like there's no like terms to add
yeah,
together.
I would
Here's,
say it's
yeah, it's with that 4x over there, huh? Let's move that 4x out of there. That will allow the 18 to be all by itself on one side. And then I'll get the x's on the other side. So subtract 4x from both sides. That's the way I would do it. 7x subtract 4x, that makes 3. So how about a 3x equals 18? All right, divide by 3. Anybody with an answer?
6.
Awesome, x equals 6. So notice with number 5, we moved the constant term around. Notice with number 6, we moved the variable around. And again, that's okay to do as well. There's no problem. Usually, if I need to move the variable, I move it first and I move it to the left. That's an easy way to do it. Well, number 7, guess what we're going to be doing? We're going to be moving both of them around. All right, so what should we do first?
Subtract the 2x.
Subtract the 2x from both sides. Perfect. So that will get all the x's on the left-hand side. (4x) subtract 2x makes a 2x. Bring down the negative 5, bring down the positive 5. In this case, what do we do next? Perfect. We have a 2x on the left. We also have that minus 5. To get rid of the minus 5, let's add 5 here. Whatever we do to one side, we got to add to the other. So there it is, adding 5 to both sides. How about 2x equals 10? Divide by 2 is perfect. And of course, we have to have one with fractions in it everywhere. Okay. I think I want to get rid of the fraction. So what number can we multiply so that 4 goes into that, 6 will go into that number, and 12 will go into that number?
4 by 12.
I think I'm going to choose 12. Is that right? Does 4 go into 12 evenly? Yep. 6 goes into 12, and 12 definitely goes into 12. So let's do this here. Remember my multiplication property, and this is kind of important right here. Remember my multiplication property says I can add this, I can multiply the same number on both sides, right? Well, I use that number to get rid of fractions here. Except instead of multiplying both sides by 12, which is what you see over here, I don't like to do that because then I have to distribute, then I got to do everything else. Here's what I do. It makes it a little easier here. I do something called method 2 in the textbook here. What I do is I multiply every single term by 12. I go 12 times x over 4 plus 12 times 1 over 6, and then 12 times negative 7/12. So notice, I am multiplying both sides by 12, right? I'm just doing it individually. Why do I do that? Is because I'm going to cancel them off individually. So notice what I'm going to do here. 4 goes into 12 how many times?
3.
3. There's my little 3. Just so I don't get too confused later on, I might as well just have them lined up individually here. Cool, so 4 goes away, 3 is on top. Let's see, 6 goes into 12 twice, so notice that all our denominators become 1s. That's cool. All the way at the end here, so 12 goes into 12 once, so that becomes a 1, that becomes a 1. That's cool. All right, what am I left with?
3x plus 2 equals minus 7.
Perfect. Yep, the 3x is from the top over here. There's the only thing that's left from this fraction or multiplication here. 2 times 1 makes it 2. The equal sign comes down, and then the 1 and 1 over here, so that means it's 1 times negative 7, negative 7. All right, then from here on out, we subtract 2 from both sides. Once you get past that step, then the rest is really, really easy. It's just that one step right there, multiplying through by the common denominator. So I got 3x is equal to negative 9. Divide by 3. And we get x equals negative 3. All right, I think that wraps up 3.2.